Hey class, today we're going to be doing section 6.24, which is paired samples, which is a matched pairs design for AP statistics, doing hypothesis testing and confidence intervals. So disregarding the paired nature of some samples can lead to an incorrect conclusion if you use a regular two-sample t-test for mu sub 1 minus mu sub 2, so the difference between two means. For example, a researcher wants to determine if physical therapy after a soft tissue injury has an effect on range of motion. The range of motion in 7 patients with soft tissue damage were recorded before physical therapy and then after physical therapy. This is a paired sample because the pre-treatment data on patient 1 will be compared to the post-treatment data on patient 1. So it doesn't really make sense to compare the pre-treatment data on patient 1 to the post-treatment data on patient 5. Like, that wouldn't make any sense. You want to keep those numbers paired for each person. Now, if we were to do this incorrectly, and we're going to look at this as an incorrect example, let's use our calculators to conduct an informal two-sample t-test and determine if physical therapy improves the range of motion in patients with soft tissue injuries. Assume the population distributions for pre-treatment and post-treatment range of motion after soft tissue injury are approximately normal. This is just going to be an informal test. I'm not going to go over all the things. We've got our two mu values. So the true or population mean range of motion pre-treatment, and then mu sub 2 is the true mean range of motion post-treatment. Our hypothesis, our null hypothesis, is that there's going to be no improvement. So if you think about improvement in range of motion, then your post-treatment data would be higher than your pre-treatment data. So that would be mu sub 1 is less than mu sub 2. That doesn't include the equalities. So that's going to show improvement in our alternate hypothesis. So in our null hypothesis, we're going to have the opposite, which is no improvement. So mu sub 1 equals mu sub 2. This is actually a greater than or equal to. If we think about the opposite of improvement, we would want to include both of those pieces. And then if we run our test, so if I go to stat, I go into edit, and then you can see I already put these values in my calculator, so you might want to pause the video and do that. Then if I were to run a two-sample t-test, I would go over to stat and then over to tests and then down to two-sample t-test. I have my data in L1 and L2. My alternate hypothesis is that mu sub 1 is less than mu sub 2. So let's go down here and calculate it. I get a t-value, t equals negative 0.614. And remember, this is super informal. If we were doing a formal test here, we would want to show the equation for our t-value. We would want to show how we get our probability. This is just an informal, just to talk about the numbers. Our probability that t is less than or equal to negative 0.614 would be 0.275. If we use an alpha level at 0.05, so alpha equals 0.05, then my p-value is much larger than alpha. So since our p-value is greater than alpha, we fail to reject H naught. So if we fail to reject H naught, we cannot conclude that what we see in the alternate hypothesis is true. So thus we lack sufficient evidence to conclude that physical therapy improves range of motion. But let's analyze the data. So look back at the actual data, and you can kind of see I've plotted it here. If we look at all the pre-treatment values and then the post-treatment values, every single one of those values except for one patient improved. So why would our data then, if we did a test, why would it show that we don't have enough evidence to conclude that physical therapy improved range of motion? We definitely do, and we should see that in our test. So the two-sample t-test appears to be incorrect, and it's because the data is inherently paired. When you do a two-sample t-test, you're looking at two independent samples. Our samples aren't independent. So, so there is a very big difference in stats. Be careful. There's a big difference between the difference of the means, so mu sub 1 minus mu sub 2, and the mean of the differences, which is what we're going to do here. So what we should have done is taken the difference, and we're going to see this in the next example, taken the difference between pre-treatment and post-treatment for each patient, and then just done a one sample t-test with the differences. Okay, so let's go to the next page here. So sampling distribution of X bar sub D. So this is the mean of the differences. D stands for differences. First, the mean of our differences equals the true mean of the differences in their sampling distribution. Remember, that's a theoretical model. If we were to get all possible samples. Number two, we've got our standard deviation of the mean of the differences is the standard deviation of our sample. So S is for sample statistics over the square root of n. So we rarely know the true standard deviation. So we will most likely just use our sample value. And the sampling distribution of X bar sub D is approximately normal if N sub D is greater than or equal to 30. So we kind of saw this before. If our sample size is at least 30, we can say that it's approximately normal, or the sampling distribution of X bar sub D is approximately normal if it is known that the corresponding population distribution of the differences is normal. All right, so a matched paired t-test for mu sub D. So remember, when we do a test, we have to name that test each time. So this is our name for this type of test. Matched paired t-test for mu sub D, paired samples. So our null hypothesis is that mu sub D equals 0. So this is always our null hypothesis, unless for some reason the problem asked us to test against the difference being a specific value. But here, this would imply, so implies no difference. If the mean of the differences is 0, then there would be no difference. An alternate hypothesis would be that mu sub D is either greater than the hypothesized value or less than or not equal to. And for our degrees of freedom, we're going to use n sub D minus 1. Our conditions for matched paired t-test for mu sub D is 1, randomization. So just like always, we always want to make sure that our sample is random. Number 2, independence between the differences. So one pair is independent from the other pairs. We're going to use randomness to show this. So we can't use the 10% rule for independence because there's no independence within each pair. We have independence between the pairs if we have random assignment or random selection. But each pair is inherently dependent. That's why they're paired. So we only have one type of independence here, and we can't use the 10% rule to do that. Number 3, the sampling distribution of X bar sub D is nearly normal. So we are going to use a histogram of the differences to tell that our sampling distribution is nearly normal, and we need to make sure that the data is paired in nature or blocked. So a researcher wants to determine if playing chess on a regular basis increases memory skills. 12 sixth graders who never played chess before were randomly selected and their memory scores were recorded. The 12 students played chess on a regular basis for the next 9 months and had their memory scores recorded again. The table below summarizes the data. Now this table, and I've already kind of plugged in the numbers here. I'll show you how to get those in an easier way. But the table shows a column for the difference. It kind of gives you that clue that we want to find the difference. The tables on your problems for your homework and on your tests or your AP exam will not show that. So you would have to recognize in this problem that these are paired datas and that you need to find the difference within each pair. So if we have 12 students and we're testing their memory skills before so pre-test and a post-test, before and after playing chess, we want those values to stay paired for each student. So to get the differences, you can do it by hand or you can use your calculator. So go to Stat, go to Edit, and then I've already preloaded our lists. So L sub 3 and L sub 4 in my calculator are the pre-test and post-test values. So you can plug those in, pause the video and do that. And then you can have the calculator calculate the differences for you. So go to the next list, go up so that it's highlighted, hit enter so that you can see it down here, and then L sub 3 minus L sub 4. So it will subtract those for you, and then you can just write them down. You don't have to worry about it. Now, you can see on our problem here, and you don't always have this information, but it's nice when you do. These pieces here, the summations of each column, are just so we can check it. So if you wanted to make sure that you type them in correctly, we could go to Stat, Calc. I'm going to go down to 2 var stats for my 2 variables, X list in L3, Y list in L4. And then I'm going to calculate that, and I can see that the sum of the X's is 7240, so that matches the information given. And the sum of the Y's is 8975, which again matches the information. So this is just to check to make sure you've done it right. If it doesn't give you that information, well, I don't know, just kind of go back through it really quick and check to make sure you got those. Okay, now that we have the differences, so I'm going to get out of this. Now that we have the differences, we're going to use these when we analyze our data. So we're no longer, it's not a 2-sample test. We're going to use 1 sample and we're going to use the difference values. So conduct a paired hypothesis t-test and determine if playing chess on a regular basis increases memory skills. So first, our mu sub d, so our parameter, is the true mean of the differences. So we have to be really careful. When we did a 2-sample, we did the true differences of the means. Now we're doing the true mean of the differences. And I know it sounds like the same thing, but it's not. Think about what we're doing. We have one mean, mu sub d, not mu sub 1 and mu sub 2. We have one mean. So it is the mean of, and then we're taking all the difference values. So it's the mean of the differences. We're not taking 2 different means and then finding the difference between the means. We're finding the mean of the differences. So it takes a while to get used to which one is which and how to say it properly, but you have to make sure to say it properly, because if you get it mixed up, it means something else. So we have the true mean of the differences between a 6th grader's pre and post memory scores after playing chess regularly for 9 months. Okay, now we want to test to see if their score increases memory skills. So this would be, so pre would be less than post, which would mean pre minus post would be less than 0. So my mu sub d would be less than 0, and this would show post score higher. So then the opposite, so that would show an increase in our scores. The opposite of that, we're going to write mu sub d equals 0, but this is really a greater than or equal to. So really greater than or equal to, kind of the opposite of our alternate. And so this would be no increase in memory skills. So either there was no difference at all, or maybe that even decreased, that sort of thing. Now the conditions for our matched pairs t-test for mu sub d. So again, we want to name our test. First condition is that if you go back up, it said that 12 6th graders who never played chess before were randomly selected. There we go. That's what we needed. So it stated that the 6th graders were randomly selected for the sample. The second one is that the data is paired, since we're comparing the pre and post test scores for each child. Third one, since the 6th graders were selected randomly, we can assume that there is independence between the pairs. So make sure you say it carefully. We're looking at independence between each student. You could do it that way too, between the pairs, or between each student. Okay. And then if you notice, I don't have at least 30. My sample size is not at least 30. So in order to determine if we meet our nearly normal condition, we want to find the histogram of the difference data. So I'm going to go, so remember my differences are an L sub 5. So I'm going to go to stat plot. I go into my first plot here. I have histogram. Oh, I have to turn my plot on. Let me turn that on. Okay, and then I want to change this to L5 because that's where my differences are. I'm going to go back into my plots and make sure everything else is off, which it is. And then I'm going to go to zoom and stat. Whoops. Let's see, plots off, second stat plot off. Okay, let me just check my stat plots again. This one's on. XList says RE. Let's try this again, L5. Okay. Oh, I want to turn this off. Okay. So plots 1 is on. I'm going to go to graph. There we go. And then I'm going to zoom stat. There we go. Okay. So here's my histogram of my data. I want to, of the difference data. So I want to just kind of sketch this really quick. Doesn't have to be perfect. And then 2 more of these. All right, so the histogram, histogram of the differences is not extremely skewed. It's pretty symmetric, and it doesn't have any obvious outliers. So the nearly normal condition is met. All right, so we've met our conditions. Now we can go through and do our test. So on the next page, there's some more room in our notes. So it didn't give us a significance value for alpha. So I'm just going to assume that it's 0.05. If you're assuming it, you want to make sure to write in that it's assumed. On our calculator now, I need to run our matched pairs test. Now, if you go to stat and tests, you'll notice there's nothing here. You can keep going down the list if you want, but there's nothing here that's going to say matched pairs test because we already did the differences. So what we want is just a simple t-test. We're going to do just a t-test. We don't have the population standard deviation, so we can't do z's. And I have my data is in L5. So we use the difference data. My mu sub 0 or my mu sub d for my null hypothesis is compared to 0. My list for my differences is in L5. If we go back, let me look at my hypothesis statements. Mu sub d is less than 0, so I want mu is less than mu sub 0 there. I've got that covered, and then I'm going to calculate this. Okay. So my t value, remember, I can't just write down this value. You won't get any credit. We need to use our formula. And our formula is our mean of our sample. So that's here. So negative 144.583 minus our hypothesized value, which was mu sub d equals 0, over our standard deviation, which is 109.741 divided by the square root of n, which in this case is 12. So we always want to write out our formula. And then we can write out our t value, which is negative 4.564. Remember, I need a degree of freedom because t's, we always need that degrees of freedom. And that's a n minus 1, so that's going to be 11, or n sub d minus 1. So then the probability, so if we think about what's going on here, I have t equals 0, I have t equals negative 4.564. I want to know the probability of this going less than based on my alternate hypothesis. So t is less than or equal to negative 4.564. And then that is going to be this p-value here. Now, I can show you how to find that. I don't know if the AP exam requires that you show work for the p-value. I've seen them say that they don't require it, but then sometimes I feel like they might. So I'm going to show you how to do that using our TCDF function. So I'm just going to write equal, so TCDF, and then I'm going to leave some space, and then I'm going to write this out. So point -4, so 0, 0, 0, 4. Okay, so TCDF, to get this probability and to show a little bit of work, we're going to go to second and then distributions. We're going to go down to TCDF. My lower value, so look at your T curve here. My lower value is going to be something really low, so that's fine. My upper value is going to be negative 4.564 for my T value. My degree of freedom is 11. And then I paste. So I'm going to write this in before I paste. I've got negative 1 times 10 to the 99th. And then I have negative 4.564 and 11. We always need to label our calculator input. So this is lower, upper, and degrees of freedom. So it's important to label. And then when I paste this, I get that same value that we saw when we ran our t-test for my probability. But now I've shown a little bit more work as to how I got that. All right, since our p-value is less than or equal to alpha, which is assumed at 0.05, I don't need to write it in here because I already wrote it up here. So it's important to make sure to state your alpha. Then we reject H naught. Thus, so if we reject H naught, let's go back. We're rejecting H naught. So we can conclude based on our evidence, our stats, that the post score is higher. So they did see improvement. So thus we have sufficient evidence to support the claim that playing chess regularly for 9 months increases memory skills for 6th graders who have never played chess before. Notice, I can't just say it increases, that playing chess for 9 months increases memory skills. I have to be really specific because they only tested 6th graders who had never played chess before. So I need to put that in there to show that I'm not generalizing it to the whole population. Okay, last part to the lesson here. We have our matched pairs T interval for mu sub d. So we've done hypothesis test. Now let's look at the confidence interval. Clear out my calculator here. Oops. Okay. So the matched pairs T interval is going to be, sorry about that, is going to be x bar sub d plus or minus some T critical value times our standard deviation of the differences over the square root of n. And the same four conditions for the test is the same as our condition as for the interval. So we still use the same degrees of freedom. And let's look at this example. A researcher wanted to determine whether chimpanzees would take advantage of the opportunity to benefit others at no cost to themselves. Chimpanzees were taught to use a lever that delivered food. One lever fed only themselves, while a second lever clearly fed themselves and an adjoining cage. The researcher hypothesized that if chimpanzees were motivated by the welfare of others, they would select the second lever if another chimpanzee was in the adjoining cage. The table below summarizes the number of times the second lever was selected out of 36 opportunities. So we have 7 chimps. Each chimp had 36 opportunities to push that lever. And we had 36 opportunities with the no chimp in the adjoining cage or chimp in the adjoining cage and how many times that lever was pushed. Now, again, you can put these values into your stat lists and then have it calculate the differences, but there's only 7 numbers. So I just did the differences by hand. So I'm going to go in here and I'm just going to go into my L1 and clear this list out. And I'm going to put in the difference values that I've calculated. So I have 2 and 0, 2, -2, -1, -3. Oops. Whoops. Not sure what happened there. 202 negative. Oh, I see. It's doing that. Okay, hold on. -2. Okay, and -1 and -3 and 0. Okay, so I have my differences in here. Now it says estimate the true average difference in lever selection using a 96% confidence interval. Assume all conditions are met. So we don't need to redo our conditions, which is nice, but we do need to make a statement saying that we're assuming all conditions are met. We need to define our parameter. mu sub d, the true mean of the differences or the true mean of the difference in the number of times a chimp feeds an adjoining cage when there is no chimp and when there is a chimp. Matched paired t interval for mu sub d at 96%. So we would write, so first I'm going to go to stat, I'm going to go to calc tests, and then I'm going to do a t interval. My data is in L1, so we're using the difference data. And my confidence level is 0.96. We wanted a 96% confidence level. I'm going to calculate this. Okay, so it gives us our information that we need to write our formula. Remember, we can't just write our interval. We won't get any credit for that. So I have, sorry, my information does not match what's on my notes. I need to check my numbers. I have, oops, that's why this first one needs to be a -2. That's where I went, -2. I wrote it down here wrong. This is a -2 difference. Okay, 0, 2, -2, -1, -3, and 0. Whoops, okay. So let's try this again. So I'm gonna go to stat, tests, t interval, and I'm gonna go back down to calculate. I'm gonna recalculate this. There we go, okay. So my x bar is -0.857 plus or minus my t critical value. So the way I find my t critical values, I find is the fastest way, is I use my t table from our AP Stats formula sheet. At the very bottom of the t table, it gives confidence levels. So a 96% confidence level. And then my t critical score, I'm gonna go all the way up until I get my degrees of freedom. Now my degrees of freedom here, df, is going to be 7 minus 1, which is 6. So I'm going to go 96% confidence level and go all the way up until I get to 6 degrees of freedom. I get 2.612. 2.612. And then my standard deviation is 1.676 divided by the square root of our n value, which is 7. Now that I've shown that I know my formula, I can just write down what my calculator is showing, -2.512 to 0.7978. All right. Now I am 96% confident that the true mean of the difference in the number of times a chimp feeds an adjoining cage when there is no chimp and when there is a chimp in it is between -2.512 times and 7978 times. And then if we think about it, it didn't ask me to make a conclusion about this, but if we think about that interval, 0 is in the interval, which means the true mean might be 0. So there might not be any difference. This doesn't really show that chimps are very, that they would take advantage to benefit others at no cost to themselves. According to this data, we can't really support that claim. All right, and that is it for today's lesson.